once again, thank you so much for joining, everyone, especially DappLion. Thank you so much for being here. Really appreciate having you here. So we have now a networking week where we had on Monday Felix covering the execution layer, and now we have DappLion on the consensus layer networking or the libp peer-to-peer protocol and its enhancements. And I'm very grateful for Lion to be here because he's one of the best people to be able to give this talk. He's an expert on consensus layer. Before he was leading the development of Lodestar. Now he is part of Lighthouse team and other consensus client, and he's mainly focused on PeerDAS, which is a big part of it, which is the networking. So yeah, he's really the expert. So thank you so much again for being here, and yeah, the stage is yours if you want to present. Yeah.
Yeah, thank you so much for having me. Yes, Mario said I'm currently developer at Lighthouse, consensus client of Ethereum. And since I joined of January last year, I've been focusing mostly on sync and PeerDAS. So a lot of networking. From my time at Lodestar, I had to become very familiar with all the specs, and I implemented. I think we did a re-implementation of this v5 partial, also of course use hub. So yeah, I'm gonna share. Let's see, how do I do it? Here, start screen sharing. The window, this one. Okay, let's tunnel vision. Let me know if you see a blackboard. Okay, perfect. Okay, so yeah, I think for this talk I wanted to basically start from the basics, just give a basic overview of what's going on P2P, on Ethereum consensus specifically. What are the basic concepts of libp2p? And then from there, I want to jump straight to the specs because, in my opinion, the libp2p specs are very well written, and they are very approachable. So I would highly encourage anyone who used to work with them just to give them a read and get familiar with them. Same with the consensus specs. There has been a lot of uh, talent and effort to make them understandable and approachable by a very wide audience. So anyone that wants to work with Ethereum or understand the thing, if you can go to the specs first, that's like the best possible source of data. It's always up to date. It's the most precise. Any other resource that derives from the spec could be outdated, wrong. So it's always good to just go to the specs first. And in case you need some help to start digesting them, then it's good to look for alternative sources. So let's start for the very basics. libp2p is kind of a competitor to DappP2p. If Mario mentioned that there has been Peter here talking about the execution stack, DappP2p is structured relatively similar. I think both of them started in the same
With,
hackathon
live,
of the same year,
lectures.
but they diverged slightly on their approach. And libp2p ended up, I think, having a more mature, comprehensive code base and approach, and that's why it was chosen for the Ethereum consensus. Because at the time when the Beacon chain got spec'd, it was an independent chain, so we had the opportunity to choose a new networking stack. But at the end of the day, most of the things are relatively similar. Like we have the same need of moving data from peers to another's in a reliable way that scales and it's resilient to attacks. So the most basic thing we need to do in P2P, consider someone proposes a block, and then we have a very large amount of peers in the network. We want this block to propagate through the network as fast as possible to everyone, assuming that not everyone is connected to everyone. So we have some sort of peer graph, peer mesh. So let's consider we have one peer here. It's going to be square. I'm not sure if Scalidro has funny figures. I think so, but I never know where they are. So the first thing these two peers need is some way to move data from one side from the other. And in terms of terminology, in libp2p, that's what's called a transport. So we need some underlying way or baseline protocol to move bytes from one side to the other. In Ethereum case, we do that over a TCP channel. So I would assume at this point, you know what TCP is. Otherwise, it's a protocol built on top of IP with ordered bytes. So the other alternative we could use is UDP, which we will talk on a second. But at least now for block propagation, we use TCP. So now that we have TCP, we have some way of moving bytes from this peer to this peer. But we need more things. Like we are not only propagating blocks, but we are also doing other things like identifying the peer, syncing, other stuff. So then the next step that we need to do is to make this connection secure. So now this TCP channel is unencrypted. It's running plain text, which is not ideal. And if we have some man-in-the-middle attack, we can get compromised, whatever. So the first thing we're going to do in terms of libp2p terminology is upgrade this transport. So what we would do is construct on top of it an encrypted transport, and we have a bunch of protocols that we can choose. In the case of Ethereum, we use noise, and what noise does is a basic handshake from one party to the other. So when you actually connect from this peer to this peer, the first thing you need to know is the IP address to start up this TCP connection. And then as a second data point, you have a public key. And with this public key is the one that you will initiate the noise handshake. So we will look at the details now, but I think it's a classic Diffie-Hellman handshake, where you know the public key, then you come up with a secret, you agree on it, and then you upgrade the connection to symmetric encryption channel. Cool. So now at this point, we have a connection where we can send encrypted bytes, but nothing else. The next thing that will become very important, as you see now, is we want to have different protocols going on at the same time. We want to have some PubSub protocol to propagate messages. We also want to have some protocol to sync or to do pings, whatever. So what we will build on top of it now is a multi-stream protocol, such that we can have in the same channel different streams of data, such that the application can say, pipe this byte of data into stream number 43, and then this channel just pumps this data to the other side, basically reusing the same connection. So in the Web2 world, in Classic LAN, TCP connections are not that expensive. Well, it depends on how browsers are implemented, but sometimes in some websites, if you need to get some data, then the website will just do another HTTP connection to go to whatever API and get an image or something. But if you want to do that, then you have to establish a new TCP connection. You need to find a new port. You need to negotiate a new HTTPS handshake. So that can be a significant amount of overhead if that has to be done over and over. So in the case of libp2p, we choose to get rid of that inefficiency and have one single transport, like one single TCP connection with every single peer, just one. And then all the data that have to change regardless of protocol, it goes through this one channel. So what the protocols we have for multiplexing are Mplex and Yamax, and then /Quick, which Quick is not technically a multiplex channel. Quick does everything. but I'll touch on that later. Like for simplicity, let's assume that it's not 2025 anymore. We are in 2020. So Quick was not here yet. So we could choose between Mplex and Yamox, but for practical terms, they do the same. Cool. And now that we have raw transport, which is encrypted and it's multiplexed, now we can start to do user application streams. So in the case that we were talking about, where we want to propagate the block, we would start a new protocol here, which would be gossipsap. And gossipsap allows us to propagate arbitrary messages in PubSub. So from the application level, we would be like your client dot gossipsap dot publish the message, and then we would reuse this existing TCP connection that opened, that is encrypted, multiplexed, find whatever stream corresponds to gossipsap, push the message, and then it gets to the other side. And then on top of it, we could add now a new substream different to gossipsap for example, blocks by range B2, and then send the peer a request and be like, hey, can you give me blocks from slot 1 to slot 16, please? And then we'll give back blocks and look at them. Cool. Let me go back here and ask you, Mario, do we want to do questions at the end or in the middle? I would be glad to stop and...
Yeah, I was just curious, why not TLS 1.3? Like, why specifically are we using noise for Ethereum's? Like, isn't TLS more widely adapted? So, yeah, I was just curious about that.
sorry, you mean TLS?
Yeah.
That's a good question. I don't know now on top of my head. Let me check. There's in the specs. So now I'm in the consensus specs, P2P interface. And then we have rationale here. Why are we using noise? I don't know now, but I would say probably because TLS may be doing too much for our needs, and noise does exactly what we need and nothing else. Like that has been the rationale for some protocols that we use, like SSZ. But as I said, like a way that Ethereum tries to adopt some existing technology for this purpose is not TLS itself, but Quick. And I'm not sure I don't know if Quick uses TLS under the hood or if it's its own encryption protocol, to be honest.
As far as I know, I think TLS is generally used in client-server models, and I don't really have much information about noise, but I think Quick also uses TLS under the hood, as far as I remember. But
Yeah,
maybe it's
yeah, makes
peer-to-peer
sense.
systems, and maybe that's why noise is maybe preferred. But I'll have to give it a read. I was thinking that you must be knowing something about why it was picked specifically. So yeah, thanks.
Yeah. Sorry, I can't give more context.
Yeah, no worries.
Yeah, hello, hi Line. My question
Hey.
is somewhere where the noise is, I feel like it should be Discovery v5. So how do they interact?
Okay, we jumped. So you're talking about this V5, right?
Yeah.
Yeah, this V5 it kind of breaks this a little bit because it's a separate thing. So this V5, from the point of view of libp2p, is actually an mostly independent protocol because from the point of view of libp2p, peer discovery happens somewhere else, and then whenever you get the peer, then the whole libp2p machine of Legos happen. So with this schematic, in the case of this B5, it will just be a different connection on a different port over UDP. And then on top of this, we just have the whole DiskB5 protocol, like no noise, no MPlex, no nothing, just DiskB5 on its own. And then I think that this B5 protocol by itself is not encrypted, but the messages are authenticated by signing key.
So they just run in parallel.
Yeah, correct.
Yeah, got it. Thanks.
Okay, awesome. Yeah, thanks for touching on this V5. Like, we're gonna get there eventually, but for now we're gonna pretend that discovery is magic and we just get peers, and then the whole stack here kicks in. So again, I want to read the specs, and now I'm in github.com/libp2p/specs. Everything is really detailedly spec'd out. Most of the basic concepts are here. And what I want to start with is this. So the connection lifecycle is exactly this structure I was talking about, where we start with a raw connection, then we upgrade into an encrypted channel, and then we upgrade into a multiplex channel. And then from there is where we can open streams. Wait, I have way too many tabs. Here, yeah. Look, here as an example, we're using TLS. So in this example, yeah, another important point. Everything goes through, whenever we want to do an upgrade or even do a user substream, we use handshake protocol. But not exactly handshake protocol, but this multi-stream protocol, which is something very basic. Whenever the initiator asks the responder, hey, I want to interact with you with this list of protocols. Which one do you select? Which one do you support? So to start with, it would open the TLS connection, and then it would ask the peer to do an upgrade. And it would say, hey, I support TLS 1.0 and noise 1.0. Then the other module will reply, yeah, let's do noise, and then we do noise. And then once this upgrade has happened, then we will do the MPlex upgrade, now going through the upgraded channel, and do another round. Hey, do you want to do, I support MPlex, I support Yamax, which one do you support? MPlex, blah. And then as a substream, the same. It just asks to open a gossip substream, and then the responder will agree, and then we will open the stream. Cool. Now let's go to MPlex. I'm not sure if I want to go through noise, but MPlex is actually, I think, quite simple and interesting to go through. So MPlex and basically any multiplexer protocol in itself, it's quite simple. The only thing we are doing is we are wrapping the messages of whatever underlying thing we want to send with some header that we attach to a specific substream. So here you can see the format. Pretty simple. We have a header with an ID, and here we would basically do a new stream if we want to open a stream. Then we send the messages, close the stream, and then reset the stream. Like, this terminology of close and reset works because you can have a channel where both ends are open. So it's constructed in a way where one, like the initiator, can send data and the receiver can send data. If you close the stream, it's only one directional. And then when it gets reset, you just close both. So yeah, as you see, the spec is super simple. Like the annoying bit of implementing this, and maybe we can touch on it later. These things are a mine for memory bugs, and you want to implement them in a way that they do as little copying as possible, because we receive a lot of data through here. Also, any of these protocols are facing adversarial players, so it's quite easy to screw up, and then yeah, they can wreck your node. And this has happened in the past. Okay, the protocol I want to spend the most time with, and I think we should go with now, and then we can take a look at the rest, is Gossip SAP. I think Gossip SAP is by far the most interesting one, and I think the most important. Also, a lot of research regarding peer DAS and scaling is on Gossip SAP itself. Like now, we have different proposals to improve this. Also, Gossip SAP 2.0 protocol. So starting from basics, where we were talking here about this example, Gossip SAP is a pub SAP protocol. So it's a protocol where you push data into users. Let's do a new one. So let's consider this example. We have one peer, two peers, three peers, four peers, five peers. And then they are meshed in this way. So now what we want to do is we want to make, so the peer on the left would publish a message. It's a publisher, original publisher. And then we want this message to propagate through the network as fast as possible. If the only thing we want to do is to propagate the message as fast as possible, then the best approach is to spam. So this peer will send a message to this one, this one, this one, and then this one will send it to, this one because it already has, but it will send to this one, and then this one will send it to this one, and this one from this one. So what we end up with is a massive amplification factor. So that the message, if we have a very high peer count, say 100, you could receive the same message from 99 peers. And then in terms of network as a whole, the bandwidth consumption for PubSub is astronomical. Like if we have an amplification factor of 100, and I don't know, like I think the end goal for Ethereum is to have these massive blocks of 32 megabytes. So it means that the whole network is like spending this massive amount of bandwidth, which makes it infeasible to have nodes at home. You will need some data center. So this amplification factor is one of the key things that Gossip SAP tries to limit with its approach. And the way it works is in Gossip SAP, we have established connections with all our peers, but we choose a smaller subset of them, and we build something that's called a mesh. So in this case, this peer would randomly select, according to scores and other stuff, this peer and this peer as its mesh peers. And at the end, what a mesh peer means is that we would push the message to the peer only to the mesh peers. And then these two and these two maybe only have, let's say, only have this one mesh peer. So then they will push to this one. This one only has this one mesh peer. And let's say as an example that this peer is not meshed with anyone, so it doesn't receive the message. Now, what happens is the name Gossip SAP comes from the word gossip. So gossip is like when you say, this person, blah, blah, blah. So you push the message directly to your mesh peers, but to everyone else, you would randomly send a list of messages that you have. So maybe this peer or this peer, after some milliseconds, they would send a list to this peer saying, hey, I have all these messages. And then this peer would be like, oh, I don't have this message, which he doesn't know it's a block, but at least it knows it's some message it doesn't have. So then this peer would reply to this one and say, hey, I want this message. Please send it to me. And then the peer would reply with the message, and then this peer gets the message. So thanks to this mixed approach, we have very fast distribution of messages through the mesh. And then the gossip protocol, so the I have, I wants, basically cover everyone else in case there's partitions or bad peers or whatever. So going back to the amplification factor, in gossip sub, it's currently expected as 8. So on average, if you have enough good peers, you will just publish to 8, and then the next peer would forward to 8, and the next would forward to 8. So this behavior is exponential. So in just like a few hops, even a network of tens of thousands of nodes get the message. And then everyone else would just gossip the I have, I wants list and get the rest. And now we'll talk a bit more on security features and how we prevent against attacks. But the libp2p team did a bunch of research and studies, and they found that with this protocol, even with very, very adversarial networks, like, I don't know, what was like 80 or 90% adversarial nodes, you still have decent propagations within seconds, which is really cool. Oh, and I think I haven't stopped for questions when we were talking about the libp2p specs. So I'm going to stop for a second. If anyone has questions about Nplex and so far gossip sub.
Like you explained that we have a different, we use Discovery 5 protocol, right? So in this, how are we connecting to Discovery 5 as a layer to get to know about our peers in here, or like, do we have our own ambient environment, or how are we discovering nodes here?
Yeah, so from the point of view of the libp2p spec, you can do whatever you want, basically. Then in practice, most consensus clients, they discover almost every single peer they have through this v5. But I think some of them have a discovery protocol with, I don't know the name, but there's a way you can find all your IPs on localhost and then try to do a discovery with them. So that would technically be a separate discovery mechanism that runs alongside libp2p and this v5 and this one. But yeah,
Okay, so the gossip sub needs to like discover the nodes, right? So it is using disk 5 for that.
yeah, correct. Yeah.
Yeah. Okay. And like, if like, are things random, or we are trying to use some distributed hash table or something of that sort of an algorithm for this discovery?
Yeah, exactly. So this v5 works with a Kademlia table, and you.
Okay.
Yeah, what you do is you do queries to peers randomly, and you try to work this table and discover as many peers as you need. So it's possible you could work the whole table and discover all peers, but that's a bit wasteful. Usually what you do is you start from a boot node, and then from there you would query some random set of peers. And then if you need more, then you just keep going. But after you have, basically nodes usually have like 100 peers. Once you have that set of peers, like usually you stop doing this discovery until you need more peers for whatever reason.
Yeah, got it. So like, because we have a DHT, we are sort of not really that problematic when it comes to the churn of things. Yeah, got it. Thank you.
Yeah, exactly.
So I wanted to ask, like, you mentioned there are two multiplexing protocols, but like, why have two? We can just have one so that we can also use one handshake, like asking which protocol to use.
Right. I think you asked why do we have two multi-stream protocols, right? Multiplexing.
Yes.
Yeah. Let me remember why. Like everything has a reason. But there are so many things and so many reasons, it's hard to keep up. Like sometimes we are not encyclopedias. But I think I think Mplex is a custom protocol developed by libp2p themselves. But it has a fundamental issue where it cannot handle back pressure. I think that was the main issue. So let's touch on this very quickly. So consider that TCP is an ordered protocol. So if the peer doesn't receive the packet number 100, it cannot receive the packet 101. So depending on how all of these protocols are implemented here, consider that the gossip sub protocol sends a lot of data, and then this peer doesn't consume it. So in terms of a stream, you have pressure from one side, like you send, and then the peer has to receive the data. If it doesn't receive the data backlogs into a queue, and you don't want this queue to be infinite, otherwise the clients would just run out of memory and explode. So usually they have some queue, let's say 1 megabyte. Once this queue is full, then what do you do? So in case of Mplex, there is no way to communicate back pressure back to the sender. So it will just backlog the underlying transport itself. So if gossip sub sends a lot of data, then the receiver doesn't yield this data, all other protocols will get blocked, which is kind of pretty bad. Then Yamox doesn't have this problem. It has a way, I think the way it works is you send window updates. So whenever you receive data, you tell your peer back, like, hey, now you're allowed to give me 1 megabyte of extra data. And unless you get this allowance, you're not allowed to send more data. And that way you can communicate back pressure on a substream level. So if gossip sub is very slow, then gossip sub will stop working, but everything else can still send data. Then what happens is Yamox is very complex. So when we started on, and I think Mplex was the preferred option because it's very simple to implement. So I think the issue was like Teku and Lodestar, and I don't remember who else, only had Mplex and not Yamox. So we had to support both at the same time. And then basically everyone took so much time to have a stable Yamox implementation because, yeah, again, like these protocols are, the spec is simple, but the implementation is very complex. So the Yamox implementations were not stable for a long time, like years. So we just keep rolling with two. And then Quick came along, and everyone was like, hey, yeah, whatever. Why do we have to bother with Yamox when we can just go to Quick? So yeah, that's the quick summary of why we have to.
So finally, we are going to move this to Quick.
Yeah. I think that's the plan. But again, like I think Quick has not well support on all the languages. So we will have to basically wait for the slowest implementation. I think JavaScript is an issue here. Like their Quick implementation is not very mature, and I'm not sure if another language. So if we basically deprecate all of this and only do Quick, then the Lodestar client is dead. And we already have a working implementation, so it's kind of a dick move to kick out a client. So unless there's a critical vulnerability on the protocols, it's not too bad to let them run.
Yeah, my question is, could you please tell a little bit about I don't want and if it's adopted already or not? And I wonder how clients update libraries. So is it a must to have the simultaneous version all across the clients or not? How it happens?
Yeah, really good point. So I would say if you can you ask this question again after we have gone through the gossip sub spec? Because I wanted to go, if you have time, through gossip sub spec 1.0, then 1.1, which is the scoring one, and then 1.2 is the introduction of I don't want. So we could talk about it then.
Okay.
Okay, awesome. So the big boy, Gossip Sub 101. Yeah, just to recap, Gossip Sub is the PubSub protocol that we use in Ethereum. It works with this dual architecture, like where we have everyone connected to all the peers, but we build a mesh with a small selection of peers, such that we have fast propagation with few peers, but because of the exponential effects of this propagation, in optimal network conditions, the message reaches everyone in a few hops. And then to supplement that, we have the I have, I want control messages to exchange these message lists and make sure that all the messages get distributed eventually through the peers. Cool. So all of this is explained here. Here we have the messages we were talking about. Mesh dependencies. Yeah. So as we're talking about, this relies on ambient discovery, which basically means somehow you find peers. In our case, it's this B5. But yeah. Then these parameters, the one that's more important for us is the D. So the D is it refers to how many peers on average, like what's the target number of peers that you forward the message to. And it also determines the total bandwidth of the network. Because in case of peer dash, for example, we rely on on Gossip Sub, heavily for sampling. And the main issue is that whatever sampling we need to do, like how much data we have to download to check that the block is safe, now we have to multiply that by 8 because of D. Cool. Okay, let me go through the control messages first. So all of these mesh architecture we're talking about, it's not global in all of Gossip Sub, but instead it is per topic. So in this like hierarchy of things, Gossip Sub is a like a substream or a protocol within libp2p itself, and then within Gossip Sub you have another degree of differentiation, which is the Gossip Sub topics. So within Gossip Sub, we can have the I don't remember the name, but the blocks topic. We can have the beacon attestation topic, and each topic has one message type for it. So whenever we need to publish some new type of data, say blob sidecar or slashing, then we would use a separate topic. Each topic has its own message type, its own validation rules, and each one of these has a distinct mesh. So maybe for the blocks topic, this peer could be meshing with this one and this one, but for the beacon attestation, we could be meshing with a different set of peers. So when we start to form this mesh is bidirectional. So let's go back to the start. So this peer just connected, and it has 0 mesh peers. But because 0 is less than 8, it wants to have more. So then it will go through the list of peers and be like, oh, you and you have really good scores. You look good to me. So I want to mesh with you. And then it will send the graphed message. And the graphed basically tells the peer. So this peer would tell this peer, hey, now I'm meshing with you. Just let you know. And then the peer can either do nothing, and then the mesh is established, or it can send a prune message rejecting this meshing. Also, you can send a prune at any time. So if the peer is misbehaving or doing things that you don't like, then this peer could tell this one, hey, prune, you're no longer in my mesh. Cool. Easy. And then these are the modes here. So I-halves are every gossip. So I think it's every heartbeat. We will talk on that later. The peer looks at all the messages it has in its cache, and then it chooses a random list, and it just sends this list random to the peer. So it would say, hey, I have these 500 messages, like just the hash. Then the peer checks against its own cache, like, do I don't have any of these messages? If it doesn't, it will send back an I want with the list of messages that it wants. So all of this works because we have this scene cache. So we have a data structure where we keep a list of message hash and the message itself for some period of time, which I think it's determined by the spec, not here, but here. So now I went back to the Ethereum consensus specs, phase 0, P2P. So phase 0 is the initial phase of the network. Almost everything is spec'd here. Like in the way the specs work is, this is the first fork, so the Genesis one, and then Altair also has a P2P interface, but this one only specifies the new things. And almost all these like basic directional and rational questions are answered here on the original P2P. So here we should be able to see, do we spec here the D or we don't? Maximum clock configuration. 1 second. Gossip subdomain. Yeah, okay. So for example, the D is 8 in Ethereum, but in the default libp2p spec is 6. So always the spec prevails. Then the heartbeat interval is 0.7. So this is the frequency at which we compute these I1 lists and we send them out. Again, there's probably a rationale for this. I think I remember this used to be 0.5 and then we changed it to 0.7. There must be a reason somewhere. Probably someone did simulations and then they figured out that this number is better to have less something. And then the Mcache, this is the important one. So expiry time that we of seen messages is, which determines how number of these messages are the ones that determine how much messages and data you keep on your cache. So this directly relates on the memory consumption of the protocol itself. Cool. Okay, I'm gonna stop again for a second. Any questions so far?
What happens when we lose a mesh peer? Does it like connect to a new one automatically, or?
Yeah, really good question. So for example, let's consider that this peer, I don't know, their computer sets on fire and then we lose the whole thing. So when you lose the TCP connection, it will unravel everything up, including gossip sub. So from the point of view of gossip sub, it would get like a disconnection, and then this peer is gone. So now this peer is under the D level. In this case, we are setting D to 2. So on the next heartbeat, so the heartbeat is not only a moment where you do the I have lists, but you do a lot of maintenance tasks. One of them would be, let me see for the blocks topic, how many mesh peers I have. Oh, I only have 1. That's not okay. I want 2. So then it will, we can check the code later, but basically there is some prioritization list of where do you go to look for mesh peers first. Let's say for simplicity, you check your peer set, you see which peers in my peer set have good score and are subscribed to the blog's topic. Then you would randomly choose one and send them a graft. And then at that moment, when the graft is acknowledged, so it does, basically the peer doesn't send a prune back, then you go back to having two mesh peers.
Yeah, I wanted to ask that on what basis this pair score is being determined, and like where is it kind of stored, and like what essentially determines your score.
Sorry, the audio quality is not excellent. I couldn't fully grasp the question. Are you asking about when peer scoring is necessary and when it's not?
I wanted to ask on what parameters do we decide these, on what parameters do we score the pairs as to whether they are a good pair or not?
Okay, really good question. And we would answer it extensively with Gossip Sub 1.1. So hold on for a second and we'll touch on that. Because Gossip Sub 1.1 is literally all about scoring.
Okay, cool.
So hi, actually I wanted to ask, like, you mentioned that the topics, and as nodes we are subscribed to topics. So is it optional to subscribe to some topics and some not, or is it compulsory to subscribe to every topic? Like, how is it decided?
Right, really good question. So on Ethereum, we have a list of topics. Let's say for phase 0, they are specced here. So even from the start, we already had what we call global topics. And global topics are topics where everyone should be subscribed to. And then the attestation subnets are topics where only interested parties would be subscribed to. So let's say for the global topics, the beacon block, every single participant in the network should subscribe to the beacon block. Then we specifically, nowhere in our code, as far as I'm concerned, we don't enforce that to be the case. So you are not required to subscribe to the beacon block. However, if you don't subscribe to these topics, we will see now, like in Gossip Sub 1.1, you have something that's called the mesh score. So when you do bad things, you get a bad score. When you do useful things like giving us new messages or giving us valid messages, your mesh score goes up. So if you don't subscribe to anything at all, then your mesh score is 0. So let's say that you have 100 peers and 99 of them, they are subscribed to everything and they give you valid messages. Eventually, their score will go up to some value that's more than 0. And the peer that's not subscribed to anything will remain at 0. Whenever you do peer rotation, this peer will just be kicked out because it's the peer with the lowest score, even though it's not negative. So we can see that in clients whenever we have a network scraper or some tooling like this. You can do that. You can just connect to a node. And so you have to have a Gossip Sub protocol. That's true. Like if you don't have Gossip Sub, then you will get kicked out immediately. But you could have Gossip Sub enabled and don't subscribe to anything. That's fine. That's legal as per the spec. But you will probably not survive for too long.
Okay, that answered my question. Thanks.
Sure.
Hey, yeah. So my understanding is that there can be quite large blocks, and I'm just curious if, like, for the last like 8 seconds of a slot, all the nodes need to be propagating their attestations. Are we seeing issues in like latency, and what are some ways that we may need to mitigate this in the future? Because they're gossiping these attestations like at a many pattern.
Right. So, sorry. So your question was if we have propagation issues with attestations themselves under a limited box or like some limited hardware.
Yeah, it's like for like large block size, like I would imagine be difficult to propagate between the nodes,
Right.
like across a distributed network around the world.
Yeah. So attestations themselves are actually already scaled in a I'm not sure what's the term, but like a quadratic network. So these pattern, as I explained, where all one message like the block goes to everyone, that applies to I think blocks and basically everything except for attestations, sync committee messages, and now the blobs. Or no. Okay, let's focus on attestations. So as you say, attestations, there are a lot of them. So we don't have one single attestation topic because that would be crazy. You would be getting like 30,000 messages per slot, but they all come in at once, like so it's too much. Instead, we have 64 channels, individual channels. So let's say channel 04 will only get 1/64th of that traffic. So a much more reasonable number. Let's say 500 attestations. Then these 500 attestations go through a specific mesh into a type of node that's called an aggregator. And then this aggregator gets these 500 messages, constructs an aggregated attestation, and then this aggregated attestation, is the one that we actually propagate in a global topic, which is this one, beacon aggregate and proof. So everyone only has beacon aggregate and proof. And then this channel has way less traffic, like 64 times less traffic than the sum of all the beacon attestation topics. So it's much more manageable. And that's why we have these two steps. So we have the block, then 4 seconds attestations, but 500 on every subnet, and then the aggregators aggregate, and then 500 messages on the global topic. And this scales really well. Like we have never had issues with attestations so far. Like blocks are the fucking annoying thing always, because it's this one thing that everyone has to get as fast as possible, which is really big, and everyone is playing MEB games and timing games, so we have limited time, and then the attestations are late. But the attestations itself has been doing great, to be honest.
Gotcha. Thanks.
Hi, hope you can hear me.
Sure.
So first of all, the Gossips sub version 1.1 does have an evaluation report, and it shows the results why 0.7 was chosen.
Okay.
But my question, what I really want to ask is, it might be quite noob, but for a heartbeat of 0.7 seconds, when the heartbeat fails, do I tell everybody else in my peers that this guy has dropped off the net, or I just simply do not send the message to this peer anymore?
That's a good question. So I would say the heartbeat function shouldn't be fallible. Like it should be impossible for it to fail. Like it should only fail under some weird internal error. And again, depends on how you architect it. But what you could do is you could have like a loop on a thread where you just wait until the next tick of 0.7 seconds and then run the heartbeat function. If it fails, you log an error and then you just try again. So if it's some weird internal bug that only happens once, then that heartbeat would not send any lists, of course, because it's error. And then on the next one, you will send them. but I cannot imagine why would that fail. Like
maybe like a delay in the network or something, network congestion, and the response was
right,
delayed.
I see. So when on the Heartbeat you decide to send an I have message, that message basically goes into a queue. So that doesn't interfere with the Heartbeat function itself. You just queuing for later, because we do something that's called piggybacking. So we don't want to waste one message just to send a control message. So what we do is we schedule the control message to be sent eventually, and then whenever we want to send an actual message with data to this peer, then we will piggyback, like attach the control messages on it.
Oh,
And
I see.
all these operations should be infallible. Like the only thing that could fail is the delivery of the message itself, because the queue is backed up, like what we were talking about with Mplex. Like if the other peer is not consuming gossip sub, then the message will just queue up. But that's not an internal error. That's something that can happen, and the application handles that gracefully.
I see. Thank you.
Sure. Okay. So I think there's a lot more details on 1.0, but I don't think they are as relevant as what we thought so far. Like, just to recap, 1.0, the basics are this dual peer grid, where we have the mesh, where you prune, start the mesh, graft, start to mesh with the peer, prune to remove them, then do the I have advanced list to gossip everyone. So the issue with this approach, just with this, is that you want to know who to peer with. So peer scoring is absolutely essential. You want to know who's acting faithfully and who's not. That's why 1.0 comes in. So 1.0 defines a very detailed and specific way to calculate scores, and then use those scores to decide when to do things. So when do you prune? Who do you graph with? Who do you send the I haves, etc. So this function looks a bit scary, but it's not. So the score function is this crazy thing, but at the end it's just all these P1, P1, P2, P3, P4, P5, P7 multiply together by some weight and then added together. We can go over them because I don't think it's that complicated. But some of them are penalties, some of them are positive things. So first one, very simple. You mesh with a peer, you mesh with them for some time, and then you reward. Basically, you're rewarding how long the peer hasn't attempted to prune you, or you guys haven't kicked each other out. Then P2 is how many messages have I seen from this peer which are nil. Like if you recall here, when you have a degree of 2, like on average, you would receive the same message 2 times. So here we reward the peer that sent the message first. I'm not 100% sure if that's exactly true. Like I think some implementations I think would reward messages that are within a specific window. So if you get the 2 messages almost identical, you will reward both of them. But I don't remember on top of my head. But this is basically to incentivize, to penalize. Let's assume that this peer is actually malicious and it's not doing anything. If this one sends the message to this one, and this one just forwards the message to this one, then we don't want to reward the forwarder. We want to reward the original publisher. So that's why the first receiver has value for us. So we want to reward people that create messages, not the ones that just forward them. Then the P3 is on. So again, this is not specifically for libp2p, but on Ethereum, some of the messages, like for example attestations, we can predict how much traffic we expect, because every epoch everyone has to do an attestation, and we have specific number of validators. We can compute how many attestations we should get from a topic on a specific rate. And then we use that variable to expect this number of messages from the peer. If you give us less than that, we will penalize you. Because what a malicious peer could do, so this guy, bad guy, very bad, is mesh with us and then censor everything. Like, do not forward any messages. Imagine that we have 8 peers and all of them censor everything. Then we would get like stuck in this black void and don't get anything from mesh and have to rely only in the iHaves. Because of this P3 penalty, everyone is giving us under the level, so the scores will go down, and then we will boot them out and get rid of the bad peers. Then P3B is basically, if you send a message that's invalid, we would penalize you, and you have less score. Message delivery rate. There's a threshold for expected messages. It's a sticky parameter. True. Sorry. So this is the one that you penalize if you don't get as messages. The P3B, let's ignore it for now. It's a bit more complicated, but it's a way to keep, like, make this score sticky if the peer disconnects. Then the P4 is the one I was talking about. Like, if you send us an invalid message, we penalize. Simple. P5, application specific. We don't use it. P6 is to penalize or correlate peers that are within the same IP prefix. Because the idea is, I think like most of the data centers and collocated servers have the same IP collocation factor. So I'm not sure if this one is just for the whole IP is the same, or if it of some IP prefix is the same. Like, I think in Lighthouse we do both, but in a way it's to, like, let's say that you have one computer and then you can have 1,000 peers in that computer and then just span the network. So what this tries to do is catch that type of attack and penalize it. And then the P7 is a special one. Like, there are some things that you can do in Gossip App that are malicious. So, for example, if you give me an I have list and then I send you an I want, I'm expecting you to give me the message. And if you don't send me the message within some time, I don't remember how that is. Is it back here? Well, there is a parameter called the delivery deadline. Let's say it's 5 seconds. So if I give you an I want and then you don't give me the message within 5 seconds, I would penalize you with a P7 penalty. Okay, I'll stop for a second. Any questions about scoring so far?
Where is this score stored?
Sorry, the what?
Where is the score stored? Like,
okay. Yeah, usually clients, they maintain a hash map with all of these numbers. So you would keep like a statistics per peer to be able to compute all of this within the Gossip App protocol itself.
Yeah, I wanted to ask, like, what if a client is offline and because of like these I have control messages, and if the client fails because of this, like, are there any provisions for those clients, like, who are offline or who are right now not part of the network?
Okay, if I understood the question, you're saying if the client is offline, then it will fail to do the I want deliveries, and then it will be downscores, right?
Yes.
Yeah. So yeah, exactly. That's what's going to happen, and that's fine. Like you don't care if the peer is faulty, if the peer is an attacker, or if the peer is disconnected. You want to have all the peers being honest and healthy and productive to you. So it doesn't matter. Like if the peer is not doing the duties that you expect from it, you have to kick it out.
Recording has stopped.
Thank you.
Oh.
So is this score only stored by us, or do we propagate this score to other nodes also?
Yeah, the score is always local. It's your subjective view of everyone else. No,
Okay,
basically
okay.
everyone is keeping a view of everyone else, but it's only local.
Okay, okay. Thanks.
If the score is stored locally, how we can kick off the mesh? Just from
Right. Yeah.
the
Yeah.
local?
Yeah, that's a good question. I don't think anyone persists the scores. I think so. When you kickstart the mesh, you just basically select a random peer, and then it will eventually converge into the most stable, reliable peers eventually. Okay. So yeah, 1.1 introduces this set of penalties. Again, the document is very extensive on the rationale, and I think sorry, I don't remember who, but there is a report from libp2p that it went in very in depth on analyzing all these cases, and it shows that 1.1 with this set of scoring parameters, it's quite reliable against very adversarial networks. Cool. Let's quickly touch on 1.2. So, or actually, one moment, I want to specify the consensus specs are a lot of information that's super relevant to networking. As we were talking here in the spec, it's very abstract about we have these topics where we get messages, but we don't specify what are the message and what are the validation rules. So that's what's happening here. So the way to read this is the name of the topic, and then the following validation might be forwarding. Yeah, this is the message type that we will send, and then this is the important bit. These are the rules, like the validation rules, we have to check per message before forwarding it. So if we have an ignore, what that means is that we just drop the message away, but we don't penalize the peer. And a reject is we throw the message away, and we consider the peer invalid, so we apply a P4 penalty, right? Yeah, we apply a P4 penalty, an invalid one. So just to make it more relevant, let's go to Electra. No, Follow. Where is Follow? Here. So in Follow, we have a new topic, the data column sidecar. And here we have a lot of conditions. So for example, if the commitments are invalid, that's considered to be malicious behavior. That should never happen. So it's a reject because we don't want to propagate an invalid message. And we know that the sender is malicious because it should never send such a message. But for example, if the sidecar is from the future, that could happen if the sender peer has the wrong clock or something, then we'll just ignore. It's not strictly malicious, and we can just ignore the message for now. Cool. Let's go to 1.2. So until now, all the messages in Gossip Sub have been relatively small. So beacon attestations, which is the highest traffic, the messages are tiny. I think on the order of less than a kilobyte or even bytes. And then blocks, before the merge, they used to be very small. Like a beacon block, I think it's just like, I don't know, 30 kilobytes. Now with transactions, they could be like 100, could be way more if they are bigger, but it's not too frequent. What has kind of break a little bit everything is blobs. So blobs are this new data type that we have since the NEP. And the issue with blobs is they are quite big. I think it's, I never remember. 496 times 32. So 131 kilobytes, which is, it's decently big. Like let's, if you don't have a very strong connection to download such a piece of data, it takes it takes some time, like let's say half a second, which could be sufficient. Okay, let's draw this. Let's imagine this peer wants to send a blob to these two peers, and this peer now is good, and this peer is our target. Cool. So these will be progress bars. So now let's say it takes half a second, but this peer is on a data center. So let's say this starts to download on a home connection, and then this is quasi instant. And then at this moment, this other starts to download. So then we have some progress. So we're spending bandwidth to download, and then this one gets first. But almost as this one gets first, then this one arrives also. So now we have basically spent twice the bandwidth to download the same message that we already had, which is kind of annoying. I think a more annoying case would be if when this one is about to complete, then this one starts to download. We also have this other race condition. So we could already have downloaded this, and this peer starts sending the message to us. So if the message on the target has already been received, then we have the seen cache. So we will just discard it. So it's wasted bandwidth. What the I don't want, what the I don't want message wants to achieve is whenever we get the first message, like this big one, then we will tell everyone else with a very short message. So it's quasi instant. Oh, no, this is will be, hey, I don't want this message. Like I already got it. So please don't send it. So then all this wasted bandwidth that we just had will not occur. Again, it depends on the timing, but for these slower peers that have a lot of scatter sends different times, it has shown that it can save some bandwidth. I'm not 100% sure, but I think that the results are a bit disappointing in terms of savings. But basically, the idea is this one. Like the moment that you get the first message, you tell everyone, hey, I already got the message. Please don't send it. So you waste these double downloads. So now, Katya, could you ask the question again?
About the libraries. Is it 1.2? Is it already in use or not yet? And how clients upgrade the libraries? Right. Are they compatible different versions or not?
Yeah, good question. So the way it works back to libp2p, when we have established transport encrypted multiplexed, then we will try to open substreams. All Gossip Sub is essential for everyone. So basically on startup, as soon as you have all of this completed, you will immediately try to open a gossip sub connection. So what you would do is you would do a multi select. Shit, I forgot. The multi-stream select. Yeah, you will do a multi-stream select protocol, and you will send gossip sub. I'm not sure if it's gossip sub or mesh sub. B1.0. Well, I think no one supports B1, but you will send B1.1 and B1.2, and probably this order. So you would be, hey, I support these two. I would prefer to use B2 if you have, but I also support B1. And then the receiving client would be, oh, I don't support this, so I will support this one. So then the client replies with B1. So in practice, what it means is clients support both at the same time. They have to, because this one is required by spec, but they can support B2 on top of it. And then whenever they connect with a client that has the same, like this, then both of them will select B2. If you find a client that only supports B1, then they will support B1. So some of the peer connections in the network will be B2, B2, B12, B12. The other ones will be B1, B1, even within the same peer.
Yeah, thank you.
Yeah, I think we got short on time, but maybe I wanted to touch briefly on 2.0, but I think that's probably too much. I think I'm decently happy. Like we covered all the basics of libp2p, connection establishment, encryption, multiplexing, and gossip sub, which are the most important protocols. Maybe very quickly I can touch on the other protocol that's very relevant, which is a very small protocol. So in the specs, we have two basic ways of moving information. So the first one is with gossip sub, which is a pub sub, but then we have what's called the reg-resp domain. So reg-resp is very simple. You send a packet, like a request, asking for something, and then you get data back. So as I was saying here, gossip sub is its own protocol at the libp2p substream level. But then we at Ethereum specify a bunch of other custom protocols, which are these ones. So for example, the blocks by range, the full name is blocks by range. Yeah, this one, for example. Or this is to get the status message, so just to check the peer. So this would be another protocol that we have at this level. And these ones are spec'd quite simply. Like this is the request and response, or for blocks. Yeah. So for blocks, for example, when we want to sync, we want to, hey, peer, give me blocks at this specific range. Blocks by range. Yeah. So hey, give me blocks in this range, and then the peer goes like here are the blocks. And again, we have a bunch of conditions that we have to satisfy. It's not as well written as gossip sub, where we have the ignore and reject, but it's kind of the same idea. We have specific rules that we have to abide by. And yeah, that's it. With these two things, it's most of the P2P architecture. Maybe ignoring TCP5 that we didn't have time to cover. I cannot hear.
Yeah, while we were discussing like saving bandwidth, like true, I don't want control signal. So this I don't want control signal like other control signals. Is it also piggybacked on top of a scheduled message? Because like if that is the case, then it would be like it would be inefficient because like the time delay would be enough for the schedule for it to be piggybacked on a scheduled message.
Right. Yeah, I'll probably check the implementation, but you're correct. Like, we don't want to hold the control messages forever. Like, probably what, again, I don't remember the implementation out of my head, but you could just wait for one heartbeat to hopefully have a message. And after that heartbeat, then you just send the control messages. But I guess that would be, that's up to the implementation. Or maybe it's spec, I don't know.
Test, is it audible now?
Yeah, we can hear you.
Oh, okay. So my second question. I have two questions. I'd like to start with the second one. So the second one would be, for block transactions, have anyone considered actually sending a preemptive message to decide whether or not to send, rather than a do not want message? The other way around, I guess.
Yes, I think that's Gossip Up V2. Like, I only read the spec once, but I think Gossip Up 2 works in that way. Like, yeah, we're not gonna go through it, but I remember that is the case. Yeah.
I see. Okay, then my second question would be, what else that what are the topics that we should read about that is not covered today?
What you should read about that it's not covered today.
Yes.
I would recommend the DSB5 protocol if you're interested in that. We didn't have time to cover. Then Gossip Up P1.1 report that we're talking about. Yeah, this one, the evaluation report. Yeah, I'll keep a list of these links here and I'll send later.
Thank you very
But
much.
this is very, I think this is fascinating to basically understand what type of adversarial environments we are defending against. Because the happy case looks very good, but this is what we want to protect against.
I see. Thank you very much.
When using RecResp, does the peer send requests to all the mesh peers, or maybe the high score peer, or how it works?
Sorry, could you repeat the first part? I didn't got it.
Yeah, when using RecResp.
Okay.
Yeah.
Yeah, that's not specified, and it's up to the implementation. In the case of Lighthouse, when we have to request blocks, so we first try to figure out who has the blocks that we want, depending on the type of sync, like lookup sync or range sync. And then we prefer peers that has the least connections possible to load balance, and then it's random. But you could have an implementation where you prioritize by score. But we believe that then that could be gamed, and you don't want to always ask the same peers. You want to have more random distribution of who gives you information.
Got it, thank you.
In the consensus specs, there is something attestation subnet count. So I wanted to ask, like, the attestations are like the subnet is created for particular block, or for each block as well. There are multiple subnets.
For attestations.
Yes.
Sorry, I think I didn't got the question. Could you say the last part?
Like for the attestation for each block, like, is the subnet created for each block, or there are multiple subnets for
Okay.
each block?
No, the questions are, sorry, the attestation subnets are long lasting. So even though you attest to different blocks, the attestation for block A on channel 33 gets sent on the same channel that attestation for block B, but still attestation 33. Because you want, so to build this stable mesh, it takes some time. Like building a mesh, it's not an instant thing. It's on the order of minutes, not on the order of seconds. So we want to have a long-lasting mesh of peers. That's why we recycle the subnets for all blocks.
So what if like in the pre-built mesh, if like that validator is not in the next epoch for that same mesh?
Right. So the mesh is mostly relevant for forwarding. Like when you publish, you actually can send the message to whoever you want because it's only the initial publisher. So there are two strategies we have now. The first one is flood publishing, where you send the message to literally every single peer. And that's what everyone did until recently. But now that we have blobs, the cost of doing flood publishing is too much. So now we just send to, I think, a selection of peers, which is the mesh peers. But you could actually find a strategy that could be different, or just send to randoms. If you are the publisher and for some reason don't have any mesh peers, that's fine. You can still publish to your topic peers. So topic peers is people you don't have you have not meshed with, but you know they are interested in the topic. For the block, that's basically everyone. For the blob subnets, that could be more of an issue. But hopefully, if you have 100 peers, you should have at least one of them that is interested in that topic. Otherwise, you can have issues. Yeah.
Yeah, sorry if I missed it, but why are publishing to blobs more expensive than blogs in terms of topic messages?
It's just amount of data. So blobs are 101 kilobytes, and we have, at the worst case now, I think 6. So that's that much data. And then blocks, I think on average are like 100 kilobytes. And also, as the previous question pointed out, everyone subscribes to the blog topic, but not everyone subscribes to the blob subnets. So that makes it more difficult. That's why we have the get blobs p1 optimization. Not sure if it's gonna show up like this. Get blobs p1. Yeah, so we recently added a new engine API endpoint where the publisher of a blog can choose not to publish blobs and expect someone else in the network to do that for them. And because of the way transactions work, that's possible. And it allows to save against this case. So if, let's say that the original publisher is a home staker and doesn't have enough bandwidth or no peers on whatever blob sidecar subnet we're talking about. Wait. I'm tripping both. Everyone subscribes to the blob sidecars. Like it's also a global topic. Everyone subscribes to that. So my previous comment does not apply. What is the issue is you want to propagate the block and blobs within 4 seconds before the attestation deadline. But on a home staker connection, the uplink is usually not good enough to do it reliably. Like it takes maybe 1 or 2 seconds, which is too slow to hit the deadline. So what the strategy we do now is we publish the block first and then the blobs. But if the blobs are too slow to publish, someone else in the network, just with the blobs, just with the block and access to a mempool, they can recreate the blobs on their own and republish. And that's what this optimization does.
Yeah, thank you.
It was great. I think we learned a lot today. Really appreciate appreciate having you here. Yeah, awesome.
Sure. Thank you. Thank you for having me.
Thank you so much. Yeah, it was great. Yeah, we learned a lot, and a lot more to study as well. So thank you so much, and yeah.
These emoji sounds are so enhanced.